So Science 10 or any grade 10 science class requires a pretty good understanding of the three subatomic particles in an atom. So we're going to review that. And this is all going to relate to ultimately using the periodic table and all the numbers in the periodic table. So starting with the subatomic particles that are in the nucleus, we have protons, which are often symbolized with a P+, because they have a positive charge. The other subatomic particle in the nucleus are the neutrons, using letter N to symbolize them, and then a 0 to represent that they have no charge. The last subatomic particle, which is not in the nucleus, which is outside, and we'll talk about the scientific discoveries quickly that led to the subatomic particles being where they are shortly, is we have electrons on the outside, E, and then minus because they're negative. Now the middle of the atom, the nucleons, are where all the mass is. A proton is approximately 1 unit or 1 atomic mass unit. A neutron is almost the exact same mass. We also counted each neutron as 1 atomic mass unit. And electrons have almost no mass. We don't count them. We treat it as 0 atomic mass units. The analogy I use is electrons are kind of like a speck of dust on an elephant. Okay, a speck of dust does have mass, but you don't need to count the specks of dust to determine the mass of an elephant. So a quick bit of Science 10 or grade 10 history lesson that led to the discovery of these subatomic particles are the work of Rutherford and Bohr. You know, Rutherford led to sort of the relative discovery of the relative positions. He shot positive alpha particles at a gold foil, which I have in yellow or gold coil, and the dotted blue are the subatomic particles coming in, and he wanted to see sort of what happened to them. Okay? If they go right through, they would just continue straight through to the black detector, and the particles would be noticed. They would fluoresce a little bit. Now, most of the particles went right through the gold foil, but a small amount, bounced off. Because the vast majority of them went straight through, it led to Rutherford creating a model of the atom kind of like this, where the mass is all in the middle, and that's what caused the bouncing off. But the vast majority went right straight through, and those that went straight through meant that the atom was mostly empty space, and we've got the electrons with no mass way on the outside. So that's where we get kind of a single planet type model of the atom. Now, we're not going to go into a lot of detail on these models. There's a lot more to Bohr's updating of Rutherford, but Bohr realized that the electrons aren't just in any particular place. They exist in discrete orbits, kind of circular pathways. Again, a planetary model is a good grade 10 type of model. Now, each of these orbits can only hold a certain amount of electrons, and our periodic table is a good way to help remember how many fit in each of these orbits or orbitals. So in the very first period of the periodic table, we've got 2 atoms, and that leads to there being 2 electrons that fit in the first energy level. The second period, we've got 1, 2, 3, 4, 5, 6, 7, 8 atoms, and there's 8 electrons in the second energy level. The periodic table has 8 atoms again, and at least for Science 10, we're going to continue to use sort of 8s all the way through. Now, Science 10 doesn't get into the complexity of electrons and orbitals due to the addition of these transition metals. So what I'm talking about kind of ignores these. And when you ignore these, you get a consistent 2 and then 8, 8, 8. And within Science 10, you're just going to be looking up to atomic number 20, which is calcium. So for Science 10 up to atomic number 20, we have 2 electrons in the first energy level, and then there are 8. 8 in the second, 8 in the third, and you won't even need to fill up the fourth energy level. So we're really going to use this Bohr model going forward in Science 10 and this lesson. So if we look at some Bohr models and count the subatomic particles for fluorine atom, which is neutral, which is no charge, and we'll look at what's different with a fluoride ion. So fluorine, this nomenclature is the atom or the element followed by the total mass. So this 19 is the mass, and the only thing that contributes mass is our protons and our neutrons. Okay? And we're going to count one each. So the element fluorine in our periodic table is atomic number 9, and that tells us the proton count. When it's neutral, it'll have no charge, but when it is charged, the table tells us it's going to be 1 minus. So those are two important pieces of information from our table to fill this out. So we have fluorine with no charge. We typically don't write the 0, but I want to emphasize it. And then we've got fluoride with a minus charge. So we're talking about atomic number 9. So that tells us a proton count. The periodic table is ordered by protons. Everything in the universe with 1 proton is hydrogen, and then 2 protons helium, 3 protons lithium, 7 protons nitrogen, and we're talking about 7 protons fluorine. The other particles can change, but the protons have to be 9. So both of these forms of fluorine have 9 protons. Now the mass is going to be what I've kind of color-coded in blue. There in the middle blue, 9 plus something has to add up to this 19, so there must be 10 neutrons. That gives us our 19. This is also fluoride ion 19, so charged, but it still has a mass of 19, so same mass, same proton count. It's just the electron count that's going to vary. So we have a neutral atom, so the positives, the protons are going to equal the electrons when they're neutral. So 9 protons, we need 9 electrons. So we can put them into our model. The first energy level has 2 electrons. So there's our 2, often referred to as 1 pair. Our second energy level, we can continue to fill up. We've got 9 in total. We've used 2 already, so there's 7 left. It can hold 8. We only have to put 7 in it. So we can put in 1, 2, 3, 4, 5, 6, 7. Okay. And this outer ring has none in it. Now your teacher may use circles or different shapes. There's nothing special about the axis that I used. If we move over to the fluoride ion, here the electrons and protons won't be the same because this is not neutral. Anytime something has a negative charge, it's because there's extra electrons. We have to use the charge and add electrons compared to what there would be when it was neutral. If something is positive, we're going to subtract electrons. So this is negative, so we're going to add electrons. It's -1, so we're going to add 1 more. So 9 protons would be 9 electrons plus 1 more to make it 1 minus. We've got 10. So if we start filling these in, we have the 2 in the middle. 10 minus 2 is 8, and we've got a nice full second energy level. And that's not a coincidence. Anytime you have an ion made, it has filled up an energy level or emptied it out. And it makes the atoms really nice and stable. And this is something you could predict really quickly. If you see that the neutral fluorine is missing 1 electron, you would expect a -1 charge. If there were 2 electrons missing in the second energy level, then you would expect a -2 charge. So that's a good example of a negative ion a neutral and a negative ion. Let's do another example, but we'll pick a metal that is neutral. So we'll look at sodium, that's neutral, and then we'll look at something that's positive. Now you don't have to memorize this. Sodium's atomic number 11, and you've got the charge written right into your table. So atomic number 11, so 11 protons plus 1, not for the atom, but for the ion. And ions will always have the outer energy level being full, either because a level got filled up or it got totally emptied. So that proton count again was 11. In both examples, the protons and the neutrons have to sum up to 23, the mass. So 11 and 12 will give us the 23. This ion also has the same mass, so 11 and 12 gives us our 23. Now for the neutral sodium metal, this would be like a piece of solid metal that you could hold, which you never see with sodium, where this is the ion you'd find in salt water. So neutral, the protons and electrons are the same. So 11 positives, we need 11 negatives. We now have an ion that's positive, and when something is positive, we're going to subtract electrons, and it's +1, so we have to take 1 away. So instead of 10, we're back down to 9. So if we put the electrons in both examples, 2 in the first, we've got 9 more. So there's our third, our fourth, our fifth, our sixth, our seventh, eighth, ninth, 10th, but we filled up the second energy level, so the 11th has to go into an outer energy level, and this isn't very stable, and it's going to want to be lost and become the ion form. In the ion form, we can see that it's emptied out, that third energy level. So 10 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Nice stable atom with full energy levels. So that's a pretty good introduction to the subatomic particles. This is one of the notations you might see, but there's another notation that I want to introduce and wrap this lesson up with. Nuclear notation uses the atomic symbol, and it puts the mass in front raised up, and it puts the atomic number down as a subscript. So if we wanted to look at something like these hydrogen isotopes, okay? Now isotopes are the same element, but they have different counts of subatomic particles, different neutron counts. So this hydrogen has a mass of 1, and the other hydrogen has a mass of 2. So the neutron count has to be different. There's more neutrons here than there is there. So to write these, and we'll do the hydrogen 1 down below. So we have to start with the symbol. So that is H. You would look that up in your periodic table. The mass is 1, and the mass number A is the superscript in front. So this is how heavy it is. That would tell us the protons, which have mass, and the neutrons. The subscript is its atomic number, and hydrogen is atomic number 1. There is no charge, so we don't see anything up here. We don't write in 0. We can quickly do the subatomic particles and talk about using this notation to get the count quickly. So 1 proton, that's our atomic number. To get the neutrons, it's the difference between these two. The total mass is 1, and there's 1 proton. Well, the 1 proton is all you need. You don't need any neutrons. The difference between those two is 0, so there's no neutrons. This is a neutral atom, so the proton count, which is 1, has to be balanced by the electron count. So hydrogen only has 2 subatomic particles with no neutrons. If we look at carbon 13, not the most common form of carbon. We would start with the C in the middle. We can quickly put in the mass number because that's there. And then you may want to check your periodic table, and carbon is atomic number 6. Now this mass that you see in the table that you'll use later in grade 10 is an average of a whole bunch of isotopes. So 12.01 is the average of the carbon 12 and carbon 13, the two types we see on Earth, and a tiny bit of carbon 14. So atomic number 6. So that's it for our symbol. Proton count, well, it's atomic number 6. It's neutral. Electrons will be 6. And the neutron count is just the 2 and subatomic particles in blue. So 6 and 7 gives us 13. Nitrogen. So N, which is nitrogen, a mass of 15. And now I left out the atomic number. You'll see this occasionally, maybe in upper year courses or university. It can be left out because we know nitrogen is atomic number 7. So even if it's missing, it's easy to look up. And that tells us our proton count. The difference between the 15 and the 7 is our neutrons. So there's 8 of those. There's our 15. And our electron count, protons and electrons are the same. Last example, we have an ion, so it's not going to be neutral. So we have lithium, and we could look up the charge, and it is +1. And you see everything in this first group is all 1+. Hydrogen, lithium, sodium, potassium, rubidium, cesium, they're all +1 when they're ionized. So we have 1+. So we have a mass of 7, and then we need our table for the atomic number, which is 3. So the proton count is 3. The neutron count is the difference between the 7 and the 3, which is 4. So there's our 7. And now the electron count. It's not going to be 3. It's either going to be an addition or subtraction of 1. Anytime something is positive, you have to subtract electrons. Okay? To make something positive, you're not actually adding positives. You can't change the protons. You can just have electrons come and go. So we're going to lose 1. And that makes it positive. So I've got a few examples for you to try. I'd encourage you to pause the video, and then I'll quickly go through the answers. Hopefully you have your own periodic table, but if you don't, hopefully you can see the one that I have pasted in here. And in about 15 seconds, I will go through the answers. So hopefully you've hit pause because I'm going to start going through these. So I'm going to write the nuclear notation and the subatomic atom count. For the following. So for sodium, 23, I already put the symbol in. So this is our mass number. And that's atomic number 11, and there's no charge. I'll just put that in for emphasis, though you should have left that out. So protons would be 11, neutrons would be 12, and electrons would be 11. And this one was done earlier in the notes. Carbon 12, we did carbon 13 already. This is a slightly lighter form of carbon. Easy to remember the subatomic particle counts for the most common form. Protons is 6. The difference between 12 and 6 is 6. And we have the plus and the minus have to be equal, so that's 6. So kind of not a nice number. Oxygen 16. So mass of 16, and oxygen is atomic number 8. Again, no charge for these top 4. So we've got 8 protons. It's neutral again, so 8 and 8. And then the difference between these two is 8. And you typically see the proton and the neutron count being very similar. Different isotopes just varying by a little bit above or below the proton count. Last, carbon-14, a pretty rare form of carbon. Our table shows us the average on Earth is 12, so this isn't a very common form. So we've got 6 protons. To keep it neutral, we got 6 electrons, and the difference between 14 and 6 is 8. Now we've got just a couple ions to do. We've got beryllium ion mass of 9. So the mass is 9. Beryllium is atomic number 4. And it's an ion, so we got to look up that charge, and it's 2+. So 4 tells us the protons. 9 minus 4 is 5. There's our 9. And the electron count. Let's see, beryllium would have had 4, but it's become +2, so it's lost 2 electrons. So it's 4 minus 2, which is 2. So the first energy level is filled. Always check your ions should have full energy levels. Last example, nitrogen. So we've got an ion again. If you see atom is neutral, ion, look it up. So we've got a mass of 12. Nitrogen is atomic number 7. And nitrogen is 3- when charged or ionized. So proton 7. The difference between 12 and 7 is 5. And now we've got a negative charge. We have to add electrons, add 3. So we would have 7, but we have to pick up 3 more. So that gives us 10. And that nicely fills the first energy level, would be filled with 2. And the second energy level would be filled with 8. And 2 and 8 gives us our 10. Okay. All ions have full energy levels. They might have gained, they might have lost. Now, which of the two above are isotopes? So isotopes are the same element, but they're a different atom. So of our periodic table of the elements, we're just looking for a name or atomic number that repeats, and we have 2 different isotopes of carbon. We have the carbon-12 and the carbon-13. So we've got the carbon-12, and we've got the 12 and 14. So hopefully that helped you improve your understanding of subatomic particles.